Loop quantum gravity is a very broad subject, and here I want to introduce the basic ideas without writing down equations. I want to give you some intuition without writing down equations. If you really want to understand the theory, of course, it's unavoidable to write down equations and dig deeper. But here I want to focus on just the basic ideas of the theory. The theory is vast. There are many things that could be said, but let me just tell you the most important aspects of the theory and maybe the most basic ones. If we consider a space, a generic space, we know that we have three dimensions of space and one dimension of time, but now let's focus on the three dimensions of space. We think of the space which is discretized into small volume elements, for example, tetrahedra, which are discretizing our space. Now, let's not focus too much on the volume that I have chosen. You can choose basically any kind of volume. In general, these tetrahedra have faces, and we can we can sketch the normals to the faces of the tetrahedra. And the fundamental idea of LQG, loop quantum gravity, is that these directions are not really exact directions. They are actually quantized directions. And let me tell you why. Let me give you the idea. From quantum mechanics, and in particular from the theory of angular momentum, we know that we get discrete values because angular momentum is an operator. It satisfies some commutation relations. To be technical, these commutation relations form the so-called algebra of the group, which is the SU2 group, but this is more technical and it's not really important here, but it will be important in the course. Since we have operators and we are discretizing momentum, and momentum is a vector, you have to think that we have vectors in general. Angular momentum is a vector in three-dimensional space, and in the classical theory you have a certain vector with three components, and this vector has a direction, not just a magnitude. So if this object becomes quantized, then it makes sense to think that it does not have a certain direction, a well-defined direction, right? So this is one point. And it tells us more about the space and the directions that you can define in space. This actually goes back to probably the 70s, if I remember well, because Roger Penrose defined the concept of the so-called spin networks, starting from considerations on angular momenta. Here we will not delve into these spin networks, but the idea is quite simple. You divide the space, the three-dimensional space, into small volumes, and we give some kind of quantum nature to each of these volumes, and we also have to define some kind of relation between neighboring volumes. This kind of relation that I'm drawing here with these lines, and they are called links in the spin networks, is defined. So these kind of links are defined by a connection. A connection, which is something that should be reminiscent of general relativity, gives you some kind of way of parallel transporting a spinner along a certain direction in space. Why do we transport spinors? Well, because spinors are related to angular momenta. So this is more technical. And let me get back to something less technical. I said that, okay, we can quantize the directions, and in general, we can also quantize the areas and the volumes of these small elements here. The areas are related to the flux that's defined by these normals because they exit the surfaces or the faces of these small elements. It is possible to define the so-called area operator and also the volume operator in loop quantum gravity. We will see the mathematical details of that. This is actually the core of loop quantum gravity. It is also the starting point because at the end of the day, this was how the theory started, with the volume operator, the area operators, and the concept of connection. So we will see that loop quantum gravity revolves around these objects. There are other important points, other important aspects of the theory. Let me mention another one that we will see in detail if you will have the patience to go through the lectures of the course. There are many hours of lectures that you can watch. You don't have to watch all of them. Some of them are unrelated and independent, but I tried my best to do justice to the mathematical aspects of the theory. It is possible to create some educational content without any equations, but to really understand this complicated theory, which is still developing as we speak, it's unavoidable to go through the math. Now, let me tell you this. In general, to define the theory of general relativity, and this is important to describe gravity, classical gravity, we start from an action that's proportional to the integral of the Ricci scalar. Then here you have the square root of minus the determinant of the metric, and then you have the four-dimensional volume element. So you have the three dimensions of space and also one dimension of time. And we will see that if we formulate the theory of loop quantum gravity in a non-covariant way, we will have to separate the spatial components, the spatial variables, from the time variable. The time variable will lose its significance, but we will see that. It will be related to the so-called ADM formalism. It's very important in loop quantum gravity. There are other ways to formulate the theory, and in the recent years, some efforts have been made to create a covariant theory where you treat time and space equally. So you discretize space and you also discretize time. But there are some aspects of the theory that can be formulated without mentioning the time component, since the time variable really loses its meaning, its significance. Anyway, if we write the action of general relativity, well, some physicists realized that written in this form, it is actually very difficult to derive a quantum theory, to write down a quantum theory. So there had to be another way to formulate the theory, and this led to different formulations of general relativity. Instead of writing down the metric tensor, so instead of using the metric tensor as the variable, g mu nu, this is the determinant of it, but it's not really important. I'm not focusing on the equations in this lecture. Instead of using this tensor, other variables are used, and these variables are also related to the intuition that I gave at the beginning of this lecture here. So you have some kind of connection, which is related to these links, quote unquote links that I did not really properly define, but never mind, we will see them. And we also have a variable related to flux, or this flux is through the phases of these small volume elements. So a reformulation of the theory is actually smart because it leads to a possible quantization of the theory, a simpler quantization of the theory. Now, there are many things that could be said in principle, but let me mention one more thing. And in particular, after reformulating and quantizing the theory, in LQG one could write down the famous equation called Wheeler-DeWitt equation, which is a functional equation that contains operators, and this was a very difficult equation to solve, so one needed the right tools to solve this equation. And in particular, one needed to be smart and write down a different formulation of GR in such a way that the Wheeler-DeWitt equation could be written in such a way that it could be solved. And let me tell you that a possible solution of the Wheeler-DeWitt equation, as we will see other concepts. This is just some small summary of it, but we will see more than this. We will see that the so-called loops solve the Wheeler-DeWitt equation. So this is where the concept of loops, and if we want to be more technical, holonomies, we will see them during the course, appear. And these loopy solutions are actually related to how you move along these links and you go back, and this is related to the measurement of the curvature of your space. In this case, we're really considering a quantized space, and this is just some details that I wanted to tell you. Some simple introduction that hopefully gives you the possibility to orient yourself while watching the lectures of the course.